Now we'll come to another very important type of events, and these are independent events. Now events A and B, they are said to be independent if occurrence of one doesn't affect the occurrence of another. So in this case, basically probability of A by B is probability of A, and probability of B by A is simply probability of B. Now probability of A by B is probability of A intersection B upon probability of B, and it is equal to probability of A, or in the same we can write probability of A intersection B upon probability of A, it is equal to probability of B. So from here we get this condition that if A and B are independent events, then probability of A intersection B, it must be equal to probability of A into probability of B. So if we have two events such that probability of A intersection B is equal to probability of A into probability of B, then we'll say these two events A and B, they are independent. So there'll be many questions in probability where either they'll give you in the question this word independent. Like three people, they're going to solve the same problem independently, or two people describing the event independently. And another case could be where you have to use logic to work out that the things are independent. Say for example, if we toss a coin and a die, outcome on the die is not going to impact the outcome of this coin. So in the questions, either it'll be given these events are independent, or you have to use your rationale to establish the fact that the given events are independent events. Now if A and B are independent, then we know that condition is A intersection B equals P into PB. Now from this condition, we can determine independence of A naught and B naught also. So if we have to write probability of A naught intersection B. Now we know that probability of A naught intersection B is probability of B minus probability of A intersection B. If A and B are independent, A intersection B is P into PB. So we can write this as probability of B minus probability of A into probability of B. So we'll take probability of B common, and then it will be 1 minus probability of A, and 1 minus probability of A is probability of A naught. So it will be probability of A naught into probability of B. So that means A naught and B, they are also independent. In the same way we can prove probability of A intersection B naught, it will be probability of A into probability of B naught. Now if we look at independence of probability of A naught intersection B naught, then we know that this is probability of A union B naught. Now we know P union B naught is 1 minus P A union B, and this is 1 minus PA plus PB minus P A intersection B. Now we can write this as 1 minus PA minus PB, and this is plus, and since A and B are independent, we can write this as PA into PB. Now this is 1 minus PA, and here we'll take PB common, so it will be 1 minus PA. Now 1 minus PA is PA naught into 1 minus PB is PB naught. That means A naught and B naught, they are also independent. So if A and B are independent, so is A naught B, AB naught and A naught B naught. Now if we talk about independence of three events, say A, B and C, we have two types of independence. First is pairwise independent, and second one is mutually independent. If ABC are pairwise independent, that means each pair is independent. So probability of A intersection B is probability of A into probability of B. Probability of B intersection C is probability of B into probability of C, and probability of C intersection A is probability of C into probability of A. But if they are mutually independent, then they are pairwise independent. That means probability of A intersection B equals probability of A into probability of B. Probability of B intersection C equals probability of B into probability of C, and probability of C intersection A equals probability of C into probability of A. And with this, we'll have this one more condition, and which is probability of A intersection B intersection C. It will be equal to PA into PB into PC. So if these three events, they are pairwise independent, we'll have these three conditions. But in this case, this probability of A intersection B intersection C, it may not be equal to PA into PB into PC. But if they are mutually independent, then we'll have this condition. And if generally nothing is given, it simply says A, B, C are independent. Then loosely speaking, we say they are mutually independent. And we can generalize this concept for n events. Say we have events A1, A2, A3 up to An. So if they are pairwise independent, then probability of AI intersection AJ, it is equal to probability of AI into probability of AJ, where I is unequal to J. And if they are mutually independent, then they are pairwise independent, that is PAI intersection AJ, it is equal to PAI into PAJ, where I is unequal to J. Every combination of three events is also independent. PAI intersection AJ intersection AK will be equal to PAI into PAJ into PAK, where I is unequal to J, unequal to K, and till we have intersection of all these events A1, A2 and AN, and it will be equal to PA1 into PA2 into PAN. So that is the difference between pairwise independence and mutual independence. And again in this, if nothing is clearly specified, then if it says these n events, they are independent, then loosely speaking, we'll treat them as mutually independent. Now here we are given two events as that P A union B naught is 1 by 6. That means probability of A union B will be 5 by 6. Probability of A intersection B is 1 by 4, and probability of A is 3 by 4. We can find probability of B, and will be 5 by 6 plus 1 by 4 minus 3 by 4, and that will be 1 by 2, 1 by 3. Now since probability of A and probability of B, they are different, so these events are not equally likely. And if we look at PA into PB, this value will be simply 1 by 4, which is same as PA intersection B. That means these two events are independent but not equally likely. That means this option C is correct. Now for two events, it is given that probability of A is 1 by 4, probability of A upon B, which is probability of A intersection B upon probability of B, it is also 1 by 4, and probability of B by A, which is probability of A intersection B upon probability of A, it is 1 by 2. Now we put the value of probability of A as 1 by 4, we'll get probability of A intersection B as 1 by 8. Now from A intersection B, we can find the value of probability of B. So now probability of B will be 4 times A intersection B, which is 1 by 2. Now PA into PB, it is 1 by 4 into 1 by 2, which is 1 by 8, and is same as P A intersection B. That means A and B are independent. And since the intersection is not 0, they are not mutually exclusive. Now if A and B are independent, then probability of A naught upon B will be same as probability of A naught, and probability of A naught is 3 by 4. That's your option C. And the same way, probability of B naught upon A naught will be same as probability of B naught, and which is 1 by 2. So the correct options are A, C and D. Now the question is, prove that if A, B and C are random events in a sample space and A, B, C are pairwise independent. So if they are pairwise independent, then P A intersection B is P A into PB. P B intersection C is PB into PC, and P C intersection A is PC into PA. And A is independent of B union C. We are given that P A intersection of B union C is probability of A into probability of B union C. Now we need to prove that A, B and C are mutually independent. That means we need to prove that probability of A intersection B intersection C is PA into PB into PC. Now first we look at this P A intersection B union C. So probability of A intersection B union C. Now if we look at their Venn diagram, now suppose this is A, this is B and this is C. Now it says A intersection B union C. That means that portion of A which is common with either B or C. That means we are talking about this region. So this P A intersection B union C, it is actually equal to probability of A intersection B plus probability of A intersection C, and since we have taken this region twice, so it will be this minus probability of A intersection B intersection C. Now we can write this as probability of A into probability of B plus probability of A into probability of C minus probability of A intersection B intersection C. Now we are given that it is equal to PA into P B union C. So it is equal to PA into P B union C, and B union C is PB plus PC minus PB intersection C. So we can write this as PA into PB plus PC minus P B intersection C, which is equal to PAPB plus PAPC minus PA, and since B and C are also independent, so it will be this PB into PC. Now PAPB will cancel and PAPC will also cancel. So from here we get this result that P A intersection B intersection C, it is equal to PA into PB into PC, which is what we need to prove in this question. So we have proved that A, B and C are mutually independent. Now in the part B it says an event A is known to be independent of the events B, B union C and B intersection C. Show that it is also independent of C. Now A is independent with B. That means P A intersection B is PA into PB. Now it is also independent with B union C. So A intersection B union C, it is equal to probability of A into probability of B union C, and also it is independent to B intersection C. So from here we can say this is PA into P B intersection C. Now again we'll simplify this. Now this is probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection C, and it is equal to PA into P, B union C, and we can write B union C as probability of B plus probability of C minus probability of B intersection C. So this is probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection C, and it is equal to PA/PB plus probability of A into probability of C minus probability of A into probability of B intersection C. Now P intersection B is PA into PB, it'll cancel, and PA intersection B intersection C is PA into PB intersection C, so it'll cancel. So from here we get this condition that probability of A intersection C is equal to probability of A into probability of C. That means events A and C, they are independent, and that's our second part. Now here the question is, of the three independent events E1, E2 and E3, the probability that only E1 occurs is alpha, only E2 occurs is beta, and only E3 occurs is gamma. Let the probability P that none of the events E1, E2 or E3 occurs satisfy the equation alpha minus 2 beta P equals alpha beta and beta minus 3 gamma into P equals 2 beta gamma. All the given probabilities are assumed to lie in the interval 0 to 1, both not inclusive. Then we need to find probability of occurrence of E1 upon probability of occurrence of E2. Now say probability of occurrence of E1, it is say A, probability of occurrence of E2, it is say B, and probability of occurrence of E3, it is C. Now the first one is only E1 occurs, that is P E1 intersection E2 naught intersection E3 naught. Now they are independent events. So this probability will be A into 1 minus B into 1 minus C, and it is equal to alpha. In the same way we can write 1 minus A into B into 1 minus C, it will be this beta, and then 1 minus A, 1 minus B into C, and this is gamma. Now we are given that none of E1, E2, E3 occurs. This probability will be 1 minus A, 1 minus B, 1 minus C, that is equal to P. Now we divide this first with fourth, we can write A upon 1 minus A will be equal to alpha upon P, and if we use component to dividend, we can write A equals alpha upon P plus alpha. In the same way, we'll write B as beta upon P plus beta and C as gamma upon P plus gamma. Now we need to find the value of A upon C. Now A upon C is alpha into P plus gamma upon gamma into P plus alpha. Now we'll get this expression from these two given conditions. So what we'll do is we'll eliminate beta from these. Now from this first one we can write beta equals alpha P upon 2P plus alpha, and from the second one we'll write beta as 3 gamma P upon P minus 2 gamma. Now we equate them, we can write alpha P upon 2P plus alpha will be equal to 3 gamma P upon P minus 2 gamma. Now this P and P will cancel. We'll get alpha P minus 2 alpha gamma will be equal to 6 P gamma plus 3 alpha gamma. Now what we'll do is we'll add 3 alpha gamma both sides. So we can write alpha P plus gamma and it will be equal to 6 gamma P plus alpha. So if we rearrange, we can write alpha P plus gamma upon gamma P plus alpha. It must be equal to 6. So value of probability of E1 upon probability of E3 will be nothing but 6, and that is the answer to this question. Now here the question is, an unbiased normal coin is tossed n times and let event even be when both heads and tails they are present in n tosses, and E2 is event that coin shows up heads at most once. Now probability of E1 is now total number of cases. Now if a coin is tossed n times, then total number of ways will be simply 2n, and favorable case will be when both heads and tails they are present. So there will be total, which is 2 to the power n, minus cases when it is either all heads or all tails, which are simply 2 cases. So this probability of E1 is 2 to the power n minus 2 upon 2 to the power n. Now we need to find probability of E2, and E2 is the coin shows up heads at most once. So that means total is 2 to the power n. Now here we have only 2 cases, either no heads, which is only one case when it is all tails, plus this case when we have 1 heads and n minus 1 tails. Now this 1 heads, it can occur at any of these n positions, so it can be done NC1 ways. So this probability of E2, it is 1 plus n upon 2 to the power n. Now we'll find this probability of even intersection E2. Now probability of even intersection E2 is both heads and tails they are present in n tosses, and there is at most 1 heads. That means we have this common case whose probability is n upon 2 to the power n. Now it says events E1 and E2, they have to be independent. We need to find value of n. Now they'll be independent if P even intersection E2 will be equal to probability of E1 into probability of E2. So we can write this as n upon 2 to the power n. It should be equal to 2 to the power n minus 2 upon 2 to the power n into 1 plus n upon 2 to the power n. Now this 2 to the power n will cancel. If we rearrange it, we can write this as n upon 1 plus n, and here 2 to the power n upon 2 to the power n will be 1, and minus 1 upon 2 to the power of n minus 1. Now we can write this as 1 upon 2 to the power of n minus 1 will be equal to 1 minus n upon n minus 1, and there will be 1 upon n plus 1. So we get this condition that value of n must be of the form 2 to the power n minus 1, it should be equal to n plus 1. Now 2 to the power n minus 1, it is an exponential function, and x plus 1, it's a straight line. So we'll have only one point of intersection when the value of n is positive. Now in this case, from inspection, we can say if we take n as 3, then it will be 2 square, which is 4, and 3 plus 1 is 4. So these two events, they'll be independent if the value of n is 3. And that is the answer to this question. Now here the question is, if A and B are independent events, then prove that probability of A union B into probability of A naught intersection B naught, it is always less than or equal to probability of C, where C is an event defined that exactly one of A or B occurs. Now first we'll define this probability of C. Now probability of C is exactly one of A or B occurs. So it will be this probability of A intersection B naught plus probability of A naught intersection B. Now this is probability of A into probability of B naught plus probability of A naught into probability of B. Now if we look at this left hand side, we can write this left hand side as probability of A union B into probability of A naught intersection B naught. Now we know that probability of A union B is probability of A plus probability of B minus probability of A intersection B. So this probability of A union B will always be less than or equal to probability of A plus probability of B. So we can write this probability of A union B will be less than or equal to PA plus PB, and here since A and B they are independent, we can write this as probability of A naught into probability of B naught. Now it will be this PA into PA naught into PB naught plus PB into P A naught into P B naught. Now clearly P A naught and P B naught, they are less than or equal to 1. And if they are less than or equal to 1, that means this is less than or equal to P A into P B naught plus P B into P A naught, which is nothing but P C. So we have proved that probability of A union B into probability of A naught intersection B naught will always be less than or equal to probability of C if A and B are independent and C is an event defined that exactly one of A or B occurs. Now here the question is, if M and N are independent events such that probability of M lies between 0 and 1 and probability of N also lies between 0 and 1, then which of the following is correct? Now if they are independent, they need not necessarily be mutually exclusive. Now the second one is M and N complement are independent. So we find this probability of M intersection N naught. Now this is probability of M minus probability of M intersection N. Now since M and N, they are independent, we can write this as probability of M minus probability of M into probability of N. Now we'll take probability of M common, so it will be this probability of M and then 1 minus probability of N. So this is Pm into Pn naught. That means M and N naught, they are independent. So option B is correct. Now if we look at this option C, then we need to find this probability of M naught intersection N naught. Now probability of M naught intersection N naught is probability of M union N naught. So this is 1 minus probability of M union N. Now this is 1 minus probability of M minus probability of N and then plus probability of M intersection N. Now M intersection N is probability of M into probability of N. Now here this is Pm naught, and here if we take Pn common, it will be again Pm naught. Now if we take Pm naught common, it will be this 1 minus Pn. So it will be Pm naught into Pn naught, and that means this option C is also correct. Now if we look at this option D is probability of M by N plus probability of M naught by N. Now if M and N are independent events, then probability of occurrence of M doesn't depend on N. So probability of M by N is simply probability of M, and in the same way probability of M naught by N is simply probability of M naught, and they are complementary events, so they are mutually exclusive and exhaustive. So this probability it is 1. So that means option D is also correct. Now question number 23 is, consider two independent events with the same probability P. The probability of occurrence of at least one of the two events is. So we'll take this probability as F, some function of P, and we'll need to find probability of A union B. So it'll be probability of A plus probability of B minus probability of A intersection B. Now both these probabilities, they are same. So it is P plus P and then minus. Now since these two events, they are independent, we know that P intersection B is P into PB. So it will be simply P square. So this probability will be 2P minus P square, which is nothing but a parabola opening downwards, which is always concave down. So it is strictly concave in P, and that's your option number C. Now here the question is, an experiment has 10 equally likely outcomes. Let A and B be non-empty events of the experiment. Now A consists of 4 outcomes. The number of outcomes that B must have so that A and B are independent is. Now probability of A, it is 4 by 10. Probability of B is, now suppose B has P outcomes, so this probability will be simply B by 10, and suppose A intersection B, it is C, which is common. So probability of A intersection B is C by 10, and this C, it is less than or equal to minimum of B and 4. Now if they are independent, then P A intersection B is equal to PA into PB. That means C by 10 will be equal to 4B by 100, or we can write 2B must be equal to 5C, or B should be equal to 5C by 2. Now since B is non-empty, the value of C cannot be 0, but C has to be an even number. So the only possible values of C in this case are either C can be 2 or C can be 4. Now if C is 2, then the value of B is 5, and if C is 4, then the value of B is 10. So B must have either 5 or 10 outcomes. That means this option D is correct. Here we are given that Px upon y is 1 upon 2. So probability of x intersection y upon probability of y, it is 1 by 2. Probability of y upon x, which is probability of x intersection y upon probability of x, it is 1 by 3, and probability of x intersection y is 1 by 6. Now using these three, we can calculate Px and Py. Now this Px will be 1 by 2 and Py will be 1 by 3. Now once we have Px, Py and Px intersection y, we can calculate Px union y. Now it will be 1 by 2 plus 1 by 3 minus 1 by 6. So there will be 4 by 6, which is 2 by 3. That means this statement A is correct. Now Px into Py, this is 1 by 6, which is same as Px intersection y. That means x and y are independent. And if they are independent, C is incorrect. Now we need to find probability of xc intersection y. Now since they are independent, we can write this as Pxc into Py. Now Px naught is 1 by 2 and Py is 1 by 3. That means this option D is also incorrect. So the correct options are A and B. Now this part B is a biased coin has probability P of coming up heads on any toss. So we have taken PH as P. When it is tossed twice, it is known that probability heads tails or heads heads is 5 by 6. Now we can write this probability as probability HT plus probability HH, and this is 5 by 6. Now since events are independent, we can write PH into PT, PH into PH, and this is 5 by 6. Now we'll take PH common, so it will be PH, and then here will be PT plus PH, and this is 5 by 6. Now tails and heads, they are mutually exclusive and exhaustive. So PT plus PH will be 1. So value of PH, which is P, is 5 by 6. So from here we'll say value of P is 5 by 6. Now it says if the same coin is tossed 3 times, then find the probability of observing exactly 2 heads. So probability of getting exactly 2 heads, this probability is 3C2, P to the power 2 and Q to the power 1. So it will be 3C2. Now what is P? P is 5 by 6. So it will be 5 by 6 square into 1 by 6. Now 3C2 is 3. So it will be 25 upon 36. And this is 1 by 6. So this probability will be 25 upon 72. Now here the question is, from each of the 3 boxes containing 3 white, 1 black. So box 1, it contains 3 white, 1 black. Box 2 contains 2 white and 2 black. And third box has 1 white and 3 black. 1 ball is drawn at random. Find the probability that we get 2 white and 1 black. So we have 3 cases. Case 1, if we have white, white and black, or white, black and white, or black, white and white. Now this required probability is, now getting a white ball from this is 3 by 4 into white from this, it is 1 by 2, and black from this is 3 by 4 plus white again is 3 by 4, black is 1 by 2 and white is 1 by 4 plus, now black in this case is 1 by 4, white is 1 by 2 and here again white is 1 by 4. Now this is 32 and this is 9 plus 3, 9 plus 3, 12, 12 plus 1, 13. So this probability will be 13 by 32, and that's your option A. Now here the question is, let A and B be two independent events. The probability that both occur simultaneously is 1 by 6. That means probability of A intersection B, it is 1 by 6. Now probability of A intersection B is probability of A into probability of B, and it is 1 by 6. Now let PA be X and PB be Y. So from here we get our first equation, and that is X into Y equals 1 by 6. And the second probability is neither occurs is 1 by 3. Now neither of them occurs means probability of A naught intersection B naught. Now since they are independent, their complements are also independent. So we can write PA naught into PB naught. Now here in this case it will be 1 minus X into 1 minus Y, and this is 1 by 3. Now we can write this is 1 minus X plus Y plus XY, and it will be equal to 1 by 3. Now X into Y is 1 by 6. Now here X plus Y will be 1 plus 1 by 6 minus 1 by 3. So it will be this 6 plus 1 minus 2 whole divided by 6, which is simply 5 by 6. Now we can write this Y as 1 upon 6x. So it will be X plus 1 upon 6x, and it will be equal to 5 by 6, or we can write 6x square minus 5x plus 1 equals 0. Now here we'll get x is either 1 by 3 or x as 1 by 2. Now if x is 1 by 3, we'll get y as 1 by 2, and if x is 1 by 2, we'll get y as 1 by 3, and this is the answer to this question. Now the question is, a student appears for tests 1, 2 and 3. A student is successful if he passes either in test 1 and 2 or tests 1 and 3. The probability of student passing in tests 1, 2 and 3 are P, Q and 1 by 2. If the probability that student is successful is 1 by 2, then which of the following is correct? Now the student will be successful if he passes in first and second and doesn't pass his third, or he passes first, doesn't pass second, but he passes third, or he passes all the 3 tests. Now all these probabilities, they are independent. So for the first one, passing the first, it is P, passing the second, it is Q, and not passing third is 1 by 2. Now for this one, this is P, not passing second is 1 minus Q, and then it is 1 by 2, or passing in all 3. So it will be this PQ 1 by 2, and it is given that this probability is 1 by 2. Now here this 1 by 2 will get cancelled. So we can write this as P plus PQ, it is equal to 1, or P into 1 plus Q, it should be 1. Now what are the possibilities? If we put P as 1, Q as 0, it is satisfied. Now if we put P as 2 by 3 and Q as 1 by 2, so this 1 by 2 will be 3 by 2, this again will be 1, so B is also satisfied. If we put P as 3 by 5, so it will be this 3 by 5, and 1 plus Q is 5 by 3, this is also true. And if we look at this, this is nothing but rectangular hyperbola, so there will be infinitely many possible values of P and Q. So all the 4 options, they are correct. Now here the question is, 2 cubes have their faces painted either red or blue. Now first cube has 5 red faces and 1 blue face, and the second cube, it has, suppose, R red faces and 6 minus R blue faces. Now it says, when the 2 cubes are rolled simultaneously, the probability that 2 top faces show the same color is 1 by 2. So either both the faces, they'll be red, or both of them, they'll be blue. Now probability that they'll be red, it is given by 5 by 6 into R by 6 plus both blue, 1 by 6 into 6 minus R by 6, and it is given that it is equal to 1 by 2. Now this is 5R minus R, there will be 4R. So 4R plus 6 will be equal to 18 or 4r equals 12, value of r is simply 3. So on the second cube, there are 3 red faces. And that's your option C. Now here the question is, assume that for every person, the probability that he has exactly 1 child, 2 children and exactly 3 children are 1 by 4, 1 by 2 and 1 by 4. The probability that a person will have 4 grandchildren can be expressed as P upon Q. Then find the value of 5P minus Q. Now this person, he can have either 1 child or 2 children or 3 children. Now if it is 1 child, probability is 1 by 4. For 2 children it is 1 by 2 and for 3 children it is 1 by 4. Now he is supposed to have 4 grandchildren. Now with 1 child he cannot have 4 grandchildren. So we'll consider these 2 cases. So if he has 2 children, then each of these 2 children can have 1, 2 and 3 children. And in the same way, for 3 children also, he'll be this 1, 2 and 3. Now he'll have 4 grandchildren if he has 2 children and then followed by either 1, 3 or 3, 1 or 2, 2. Or he has 3 children and then he can have 1, 1, 2. So it could be 1, 1, 2 or 1, 2, 1 or 2, 1, 1. Now this required probability will be, now probability of having 2 children, it is 1 by 2 into now 1 and 3. 1 and 3 is 1 by 4 into 1 by 4. So it will be 1 by 16. 3, 1 is also 1 by 16. And then 2, 2 is 1 by 4. Plus probability of 3 children, it is 1 by 4. And then 1, 1, 2. 1, 1, 2 is 1 by 4, 1 by 4 and 1 by 2. And that will be 1 by 32. And there will be 3 cases. So it will be 6 by 32 plus 3 by 128. Now we simplify this, it will be this 128, it will be this 27 upon 128. And that's the value of P by Q. Now we need to find the value of 5P minus Q. So it will be 5 into 27 minus 128 and that will be simply 7. So answer to this question is 7. Now here the question is, each of the n passengers sitting in a bus may get down from it at the next stop with probability P. And moreover, at the next stop, either no passenger or exactly 1 passenger boards the bus. The probability of no passenger boarding the bus at the next stop is P0. Find the probability that when the bus continues on its way after the stop, there will be n passengers in the bus. Now there will be 2 cases. Case 1, when no passenger gets out and no passenger gets in, or it will be this case where 1 passenger gets out and 1 passenger gets in. Now this required probability, say PA, will be given by this first case when no passenger gets out. Now each passenger gets down with the probability P. So probability of not getting down will be 1 minus P. So it will be 1 minus P, 1 minus P, 1 minus P for all the n passengers. So this probability will be 1 minus P to the power n into no passenger board the bus. So this probability of no passenger boarding the bus is P0. So it will be 1 minus P to the power n into P0 plus the second case. Now one of these passenger gets down the bus. Now which passenger or these n we can select any one in NC1 ways. Now probability of his or her getting down is P And for the remaining not getting down, it'll be 1 minus p to the power n minus 1. Now one person boarding the bus, it'll be simply 1 minus p naught. Now in this case, we can take 1 minus p to the power n minus 1 common. So it'll be 1 minus p to the power n minus 1. And here it'll be 1 minus p into p naught plus n p into 1 minus p naught. And that is the answer to this question. Now here the question is, the probabilities that 3 men hit a target are respectively 0.3, 0.5 and 0.4. Each fires once at the target, and assume that these 3 events are independent. A is find the probability that they all hit the target. So for this A and this first part where all 3 of them they hit the target, it will be simply product of all the probabilities, which is 0.3 into 0.5 into 0.4, which is simply 0.06. So probability of all 3 hitting the target is nothing but simply 6%. And the second part where it says all 3 of them they miss the target, it will be simply first one missing it is 0.7. For second one it will be 0.5, and for third one it will be simply 0.6, and there will be 0.21, which is 21%. So there's 21% chance that all 3 of them they're going to miss the target. Now for this B part, it says find the probability that the target is hit at least once. Now at least once is 1 minus target is not hit, and it'll be simply 1 minus the probability that all 3 of them they miss the target. So it'll be this 0.7 into 0.5 into 0.6, which is 1 minus 0.21, which is 0.79, which means there is a 79% chance that at least one of them is going to hit the target. So this is B1. Now B2 is exactly once. Now for exactly once, we have 3 cases, and let us say these 3 people, they are A, B and C. Now this first case, when A hits the target but B and C they fail to hit it. Second case, when A could not, B hit the target and C did not. And then this third case where A and B they miss the target and C hits the target. Now this probability will be given by probability of A is 0.3. Now this is 0.5 into 0.6. Now this is 0.7, 0.5 into 0.4, and this probability is 0.7 into 0.5 into 0.4, and this comes out as 0.44. That is, there is a 44% chance that exactly one of them is going to hit the target. Now this third case, it says if only one hits the target, what is the probability that it was hit by this first man? Now this becomes condition for Bayes theorem. Now in Bayes theorem, we have this entire case. Target is hit by exactly one man. Now this one man, it has to be this first man, which is A. So in this case, what we'll do is, for this probability, we'll take this case in the numerator, so which is 0.3 into 0.5 into 0.6, and then we'll divide it with this total case, which is 0.44. Now this is 0.09 upon 0.44. So this required probability is 9 by 44. Now here the question is, 3 shots are fired independently at a target in succession. The probability is that the target is hit in the first shot is 1 by 2, in the second 2 by 3, and the third shot is 3 by 4. In case of exactly one hit, the probability of destroying the target is 1 by 3. In case of exactly 2 hits, it is 7 by 11. And in case of 3 hits, it is 1. Find the probability of destroying the target in 3 shots. Now we have 3 separate cases. Case 1, when the target is hit exactly once. Now the target is hit exactly once, then either it will be hit by this first shot, then in that case it will be 1 by 2. Then these 2 shots, they're going to miss. So it will be this 1 by 3 into 1 by 4. or second one hits the target while the other two they miss. So it'll be this 1 by 2 into 2 by 3 into 1 by 4, or this third one. So it'll be this 1 by 2 into 1 by 3, and for this third one it'll be 3 by 4. Now it is given that when the target is hit exactly once, then the probability of destroying the target is 1 by 3. So it'll be multiplied with this 1 by 3 plus. Now the second case when exactly two of them hit the target. Now it could be first two. So we can write 1 by 2 into 2 by 3, and the third one misses. So it'll be 1 by 4, or second and third. In that case, it'll be 1 by 2 into 2 by 3 into 3 by 4, or first and third hit the target while the second one misses. So it'll be this 1 by 2 into 1 by 3 into 3 by 4, and probability of it getting destroyed in two shots is 7 by 11, and plus this third case when the target is hit by all three. So if the target is hit by all three shots, it'll be 1 by 2 into 2 by 3 into 3 by 4, and then if all the three shots hit the target, probability of destroying the target is simply 1. So we'll multiply it with 1. Now this is 12, 24, and this is 6. So it'll be 6 by 24 into 1 by 3 plus, now this is again 24, and this is 6, 9 and 11. So it'll be 11 by 24 into 7 by 11, and plus this is 1 by 4. Now here 11 will cancel, and here it'll be this 2, and this is 1 by 12. So this required probability will be 1 by 12 plus 7 by 24 plus 1 by 4, and it'll be this 24, 2 plus 7 plus 6. So it'll be simply 15 by 24, and which is 5 by 8. So the probability of destroying the target in 3 shots is 5 by 8. Now here the question is, a train consists of n carriages, each of which may have a defect with probability p. All the carriages are inspected independently of one another by two inspectors. The first detects defect with probability p1 and the second with probability p2. If none of the carriages is found to have a defect, then the train departs. We need to find the probability of the event. The train departs with at least one defective carriage. Now what we'll do is we'll consider any one carriage. Now suppose it is defective. Now probability of this coach being defective, it is P, and this defect, it's get undetected by both the inspectors. It is given by this probability. Now first one detects it with the probability P1, and if he doesn't detect it, it'll be 1 minus P1, and the same way if second one doesn't detect it, it'll be 1 minus P2. So for any coach to have a defect and still goes undetected, this probability is P into 1 minus P1 into 1 minus P2. So this is the probability that the carriage has a defect and it is undetected. Now the probability that this carriage, it does not have a defect, it is 1 minus P into 1 minus P1 into 1 minus P2 in case it has departed. Now the probability that or these n cages, none of them they are defected, it is given by this 1 minus P into 1 minus P1 into 1 minus P2 n times. So there will be 1 minus P into 1 minus P1 into 1 minus P2 to the power n. So this is the probability that the train departs with none of the defective carriage. Now we need to find the probability that the train departs with at least one defective carriage, and this probability will be 1 minus when none of them is defective. So it will be 1 minus, and this is 1 minus P into 1 minus P1 into 1 minus P2 whole to the power n, and that is the answer to this question. Now here the question is, 3 students A, B and C tackle a puzzle together and offers a solution upon which majority of the three agrees. The probability of A solving the puzzle correctly is P. So probability that A solves the puzzle, it is P. Probability of B solving the same puzzle correctly is also P. So probability of B solving the puzzle, it is also P. And C is a dumb student who randomly supports the solution of either A or B. So this C, it is only there to choose either of the two solutions, either from A or from B. Now there is one more student D whose probability of solving the puzzle correctly is once again P. So probability that D is going to solve the problem or the puzzle, it is P. Now out of 3 members team A, B, C and 1 member team D, which is more likely to solve the puzzle correctly. Now if we look at this team A, B and C, then probability of they are getting the puzzle correctly will be this probability when A gets it correct, B gets it correct. In that case, C is going to support both of them. Plus A gets it correct, B doesn't get it correct, and C supports A. Plus probability that A doesn't get it right, but B got it right, and then C supports B. Now probability of A intersection B, it is probability of A into probability of B. Since the two events, they are independent. So this probability will be simply P into P. Now this is P, and then probability of B naught will be 1 minus P, and C supporting A, it is 1 by 2. And the same way, again these events are independent. PA naught will be 1 minus P, probability of B will be P, and C supporting B will be simply 1 by 2. So it will be P square, and here will be P into 1 minus P, which is P minus P square. So the probability that the team is going to get it right, this probability is P, and probability that D is going to get it right is also P. So both the teams are equally likely to solve the puzzle correctly. So there is no advantage to any of the teams. Now here the question is, 6 different balls are put in 3 different boxes, none being empty. The probability of putting the balls in equal number is. Now we have 3 boxes and they're different, say first, second and third. Now how can we put the balls in them so that none of them is empty? Now what we'll do is, first we'll figure out in how many ways we can distribute the balls so that none of the box is empty. Now either it could be 4, 1, 1, or it could be 3, 2, 1, or it is 2, 2 and 2. So these are the 3 possible cases. Now first we'll distribute them as 4, 1, 1. It can be done in factorial 6 divided by factorial 4. Now since we have 2 ones, it will be this factorial 2, and then we can arrange these 3 groups in 3 boxes in factorial 3 ways. Now this is 13 to 3, 90. So there are 90 ways possible. Now how about 3 to 1? It will be this factorial 6 divided by factorial 3, factorial 2. Now again we have to distribute them in 3 boxes. Now it will be this factorial 3 gets cancelled. Then it will be this 360. And finally this is factorial 6. Then factorial 2 3 times divided by factorial 3, and then we'll multiply it with factorial 3, which will get cancelled. Now here it will be again 90. Now we need to find the probability that the balls are put in equal numbers. So this required probability will be, this is the favorable case, 90 upon total. Now total will be 90 plus 90, 180, 180 plus 360, and that will be 540, which is 1 by 6. So this A, it matches with Q. Now the second one is, 6 letters are posted in 3 letter boxes. Find the probability that no letter box is empty. Now we have to find the probability that no letter box is empty. Now first we'll find total number of ways of distributing these 6 letters in these 3 letter boxes. Now for each letter we have 3 choices. So total number of ways of distributing these 6 letters in 3 boxes is 3 to the power 6. Now in how many ways we can distribute them so that no letter box is empty? Now this case is similar to this first one, where we have 6 different balls in 3 different boxes such that none of them is empty. Now total number of ways of doing it is 540. Now in this case, this 540, it becomes our favorable case. So this probability will be this 540 divided by 3 to the power 6. Now 9, so this is 60 and this is 3 to the power 4. Now this is 20 by 27. So this B, it matches with B. Now the third one says, two persons A and B throw 2 dice each. If A throws a sum of 9, then probability of B throwing a sum greater than A is. Now we need to find this conditional probability that B throwing a sum greater than 9 if A has scored 9. Now this probability is probability of A throwing 9 and B throwing sum greater than 9 divided by probability of A throwing 9. Now we'll get 9 in a throw of 2 dice if we have 3, 6, 4, 5, 5, 4 and 6, 3. So this required probability of A9 will be simply 4 by 36. Now we need to find this intersection that A scores 9 and B scores the sum which is greater than 9. Now the sum greater than 9 could be either 10 or 11 or 12. Now we get 10 if we have 4, 6, 5, 5 and 6, 4. 11 is 5, 6, 6, 5 and 12 is 6, 6. So we have 6 cases here. Now A9 intersection B as greater than 9. Both these events, they are independent events. So there is no correlation between A getting 9 and B getting sum greater than 9. So it will simply be probability of A9 which is 4 by 36 into probability of B getting sum greater than 9 and which is 6 by 36. So this required probability will be simply 1 by 6. So that means the C, it matches with Q. And then it is if A and B are independent and PA equals 0.3 and P A union B naught, it is 0.8, find probability of B. Now we know that we can write probability of A union B naught as probability of A naught intersection B naught, and this is 0.8. So from here we can write probability of A naught intersection B will be simply 0.2. Now this is probability of A naught into probability of B and this is 0.2. Now probability of A naught, it is 0.7. So probability of B will be simply 2 by 7. That means this D, it matches with S. And that is the answer to this question. Now the question is, a die is weighted such that probability of rolling the face number n is proportional to n square. Now this die is rolled twice, yielding the numbers A and B. Find the probability that A is less than B and this probability is P. Then find the value of graded function of 2 upon P. Now probability of getting any number n, it is proportional to n square. Now suppose this constant of proportionality is K. So we know that summation Pn, where n varies from 1 to 6. So it will be this summation K n square, where n varies from 1 to 6, it will be 1. Now this is K and this is n plus 1, 2n plus 1 divided by 6, and it is equal to 1. So the value of K is 1 by 91. So this probability of getting n on any dice, it is n square by 91. Now it says a die is rolled twice, yielding the numbers A and B. The probability that A is less than B is. Now if A is less than B, then the possible combination that we have here is 1, 2, 1, 3 up to 1, 6, and here will be this 2, 3, 2, 4 up to 2, 6, 3, 4, 3, 5, 3, 6, 4, 5, 4, 6, and then 5, 6. So these are the all favorable conditions for A and B such that A is less than B. Now we'll start writing this probability P. Now this probability P will be
Now in each we get this 91. So it will be this 1 by 91 into 1 by 91. And then for 1 into 2, it will be this 1 square into 2 square. So there will be this 4. Then 1 square into 3 square, 9, 16, 25 and 36. Plus, now here we have 2 square, which is 4. And then 3 square plus 4 square, 5 square and 6 square. So there will be 9, 16, 25 and 36. Plus, now here we have 3. So it will be this 9 and then 16 plus 25 plus 36. And then we have this 16, which is 5 square plus 36. And then finally it will be this 25 into, and the 6 square is 36. Now this value will be 3003 upon 91 into 91. Now it says find the value of greatest interior function of 2 upon p. So we need to find greatest interior function of 2 by p. Now it will be this 2 into 91 into 91 divided by 3003. Now 91 divides 3003 and there will be this 33. Now 2 into 91 divided by 33, there will be 5.5 something. So greater function of this will be simply 5. So answer to this question is 5.
Now here the question is 4 fair dice D1, D2, D3 and D4 each having 6 faces numbered 1 to 6 are rolled simultaneously. The probability that D4 shows a number appearing on one of D1, D2 and D3. Now here we have to consider 3 cases. Case 1, when D1, D2 and D3 they have same number, say x, x and x. Now D4 must show a number appearing on one of D1, D2 and D3. Now in this case D4 must also have x. So that means all the 4 dice they'll show the same number. Now this probability will be given by 6 upon and then 6 into 6 into 6 into 6. So there will be 1 upon 216. Now we have the second case when 2 of the die they'll show the same number, say x, and third die it shows y. Now 2 same numbers, it can be any one out of 6c1 and then one distinct will be this 5c1. And once we have x, x and y, it can be arranged among d1, d2, d3 in 3 ways. So now we have x, x and y. Now in this case, this d4, it can either be x or it can either be y. So we have 2 favorable cases for d. So this will be 6 into 6 into 6 into 6. Now this 6 will cancel. This 6 will also cancel. So this probability will be 5 by 36. Or we can also write this as 30 by 216. Now we'll have this third case when all the 3 numbers they are distinct. So it will be this x, y, z. So we have to choose 3 numbers which can be done in 3 ways. Now these 3 numbers they can be distributed among 3 dice in factorial 3 ways. And this d4 it can take any one of these 3. So it will be this 3c1 divided by 6 into 6 into 6 into 6. So this factorial 3 will cancel. Now this is 20 into 3, 60. So it will be this 60 upon 216. So this probability that D4 shows the same number as one of the 3 dice will be sum of all these 3 cases, which is simply 91 upon 216. And that's your option A. Now here the question is, let E and F be 2 independent events. The probability of exactly one of them occurs is 11 by 25 and probability of none of them occurring is 2 by 25. If PT denotes the probability of occurrence of the event T, then we have to find the value of PE and PF. Now suppose PE is E and PF is F. Now probability exactly one of them occurs is probability of E intersection F naught plus probability of E naught intersection F, and this probability is 11 by 25. Now since they are independent, so it will be this E into 1 minus F plus F into 1 minus E, and it will be 11 by 25. So we can write this as E plus F minus 2 E into F will be 11 by 25. And the next one is none of them occurring. So none of them occurring is probability of E naught intersection F naught, and will be this 2 by 25. Now this is 1 minus E into 1 minus F, and it is 2 by 25. So we can write this as 1 minus E minus F plus EF will be 2 by 25, or E plus F minus EF will be 23 by 25. Now if we subtract this first from second, we can write E into F as 12 by 25 and E plus F as 35 by 25. Now this is 7 by 5. Now their product is 12 by 25 and their sum is 7 by 5. Now this is 2 into 6, 4 into 3. So we can write this as 4 by 5 into 3 by 5, and here will be this 4 by 5 plus 3 by 5. So one of them is 4 by 5 and the other one is 3 by 5. That means this option A or this option D. So the correct options are A and D.
Today we'll discuss Indian Statistical Institute, that is ISI's BMath and BStat 2018 paper. Link to that paper, I'll provide it in the description below. Now again, questions in this paper, they're absolute delight. So let us get on with the first question. And the first question is, let x be a number that lies between 0 and 1 by 6. When a certain biased die is rolled, a particular face F occurs with probability 1 by 6 minus x, and its opposite face occurs with the probability 1 by 6 plus x. So we have this die where these two opposite faces, one of the probability is 1 by 6 minus x, and for the other it is 1 by 6 plus x, and for the remaining four faces the probability is simply 1 by 6. Now it also says, recall that opposite faces sum to 7 in any dice. So that means these two faces, it can be either 1 or 6 or 2 or 5 or 3 or 4, or their ordered pairs, that is 6 1, 5 2 or 4 3. Now it says if the probability of getting the sum 7 is 13 by 96, we need to find the value of x. Now we need to find probability of getting the sum 7. So probability of getting the sum 7 is when we get either 1 6 or 6 1 or 2 5 or 5 2 or 3 4 or 4 3. Now out of these 6 pairs, there is exactly one pair with these probabilities 1 by 6 minus x and 1 by 6 plus x, and for the remaining 4 pairs it will simply be 1 by 6 and 1 by 6. So I can simply write it as 2 times 1 by 6 minus x into 1 by 6 plus x, and then plus 4 times it will be 1 by 6 into 1 by 6, and they have given that this probability is equal to 13 by 96. So I can write it as, so this is 2 and this is 1 by 6 square minus x square, and then plus 4 by 36 equals 13 by 96. So here will be 2 by 36 plus 4 by 36. 6 by 36 is simply 1 by 6 minus 2x square, and this is 13 by 96. So I can write 2x square as 1 by 6 minus 13 by 96. So it will be 96, and then this is 16 minus 13. So I'll write it as 2x square equals 3 upon 96, which is x square equals 1 by 64. So this value of x should be 1 by 8. That's your option number A.
Fourth question is, a policeman fires 3 bullets on a dacoit. The probability that dacoit will be killed by 1 bullet is 0.7. What is the probability that dacoit is still alive? The dacoit is still alive if none of the bullets hit him. The probability that dacoit is still alive will be this P naught whole cube. So it will be 0.3 cube and there will be 0.027, and that's your option C. Now here the question is, a casting manufacturing company supplies metallic casting to an automobile company. The automobile company inspects every casting and rejects the casting if found defective. Now suppose a batch of 940 casting is supplied by manufacturer containing 70 defective. What is the chance that first and second casting inspected are defective and third is good? Now if first is defective, then its probability will be 70 divided by 950. Now for second to be defective, we'll have 69 by 949. And if third is good, we'll have 950 minus 70, and there'll be 880 by 948. And this value is 0.000497, and which is none of the above, and that's your option D. Next the question is, box 1 contains 3 cards bearing numbers 1, 2 and 3. Box 2 contains 5 cards bearing number from 1 to 5, and box 3 contains 7 cards bearing number from 1 to 7. A card is drawn from each of the boxes. Let xi be the number on the card drawn from the ith box. Now the first one is the probability that x1 plus x2 plus x3 is odd. Now we have 3 boxes, 1, 2 and 3. And the first one we have 3 numbers, 1, 2, 3. Here we have 1, 2, 3, 4 and 5. And here we have 1, 2, 3, 4, 5, 6 and 7. Now from this one we have selected x1. Here we have selected x2. And here we have selected x3. Now first one is we need to find the probability that x1 plus x2 plus x3 is odd. Now it will be odd if all 3 of them they are odd, or we get odd from one and then even from other 2, or it could be odd from second, or it could be odd from third. So these are the 4 possible cases. Now getting an odd from this first box, it is 2 by 3. Odd from second is 3 by 5, and odd from third is 4 by 7. Now plus odd from first 2 by 3, even from second 2 by 5, even from third 3 by 7. Now even from first 1 by 3, odd from second 3 by 5, and then it will be this 3 by 7 plus the even is 1 by 3, it is 2 by 5, and then here will be this 4 by 7, and that's the required probability. Now this probability will be 24 plus 12 plus 9 plus 8 divided by 105. Now this is 20, 44, 44 plus 9 is 53. So this probability will be 53 upon 105, and that's your option B. Now the second part is we need to find the probability that x1, x2, x3 are in AP. Now it can be an AP with common difference of 0. In that case we'll have 1, 1, 1, 2, 2, 2, and 3, 3, 3. If we say common difference of 1, then we can have 1, 2, 3, 2, 3, 4, 3, 4, 5. If we take common difference of 2, then we'll have 1, 3, 5, 2, 4, 6, 3, 5, 7. And if we consider common difference of 3, then we'll have 1, 4, and 7. Now t equals to 4 is not possible. Now there is one more case when the value of d is -1, and there we can have 3, 2, and 1. So these are the possible cases for an AP. Now it'll be this 3, 3, and 3, 9, 9 plus 2, 11. So total number of ways in which we can choose x1, x2, x3, they are in AP, it is 11. So this required probability, it will be 11 upon. Now total number of ways of choosing them. Now for the first one it is 3, for the second one it is 5, and then it is 7. So it will be this 11 upon 105, and that's your option C. Now the next one is the minimum number of times a fair coin needs to be tossed so that probability of getting at least 2 heads is at least 0.96. Now getting a heads, it is success. This probability is 1 by 2, and getting a tails is 1 by 2. And suppose n is number of times we are tossing this coin. Now we need to find this probability that x is greater than or equal to 2. Now we can write this 1 minus probability of x less than 2. So it will be this 1 minus probability x equals 0 minus probability x equals 1. Now it says this probability is at least 0.96. So we can write 1 minus, now probability of x equal to 0 is nc0 1 by 2 to the power n minus nc1 1 upon 2 to the power n, and it should be greater than or equal to 0.96. Now we can write this as n plus 1 upon 2 to the power n. It should be less than or equal to 0.04. Now we can write this as 100 into n plus 1 should be less than or equal to 2 to the power of n plus 2. Now this is greater than 100, so that means 2 to the power n plus 2, it should be greater than 100. So basically value of n, it should be greater than or equal to 5. Now we take n as 5. Now it will be this 600, and here will be this 2 to the power 7, which is 128, not possible. So if we take 6, now since it is greater than 500 here, so here this value, it should be at least 8. So if we try n as 8, then we'll get 8 plus 1, 900, and which is less than 2 to the power 10, which is 1024. So minimum value of n is simply 8. So the minimum number of times this fair coin must be tossed is 8, and that is the answer to this question. Now the second part is two whole numbers x and y are randomly selected. Find the probability that x cube plus y cube is divisible by 8. Now what we can do is we can categorize all the whole numbers in 8 categories. Either numbers which are multiples of 8, or leaving the remainder 1, 8k plus 2, 8k plus 3, 8k plus 4, 8k plus 5, 8k plus 6, and 8k plus 7. Now if both x and y they are even, then in that case x cube will be divisible by 8 and y cube is also divisible by 8. So if both of them they are even, then in that case this number x cube plus y cube will be divisible by 8. So if we take all these cases when x and y they belong to either of these 4, then this sum, it is divisible by 8. Now, what if x and y, they are odd? Now, if we look at x cube plus y cube, x cube plus y cube will be x plus y, and then it will be x square plus y square minus xy. Now, if both x and y, they are odd, then x plus y will be even, x square will be odd, y square will be odd, and x into y will also be odd. So this entire expression will be an odd number. So when x and y, they are both odd, then this x cube plus y cube, it can only be divisible by 8 if x plus y is divisible by 8. Now, it will be divisible by 8 when we have one of the numbers from 8k plus 1 and it's get added to 8k plus 7. So we have this one category where we have 8k plus 1 and 8k plus 7, or this other category when we have 8k plus 3 and the other one should be 8k plus 5. So these are the two possible cases. Now if one of them is odd and the other is even, so this is odd and this is even, so it will be an odd number, so it cannot be divisible by 8. So we have two cases. When both of them, they are even, then in that case it will be divisible by 8, and if both of them, they are odd, they must be either this form or this other form. Now we'll start writing this probability. Now this probability will be equal to, first case when both of them, they are even. Now the first one is even, then it can be 4 cases out of any 8 cases, so it will be simply 1 by 2. Other one will also be 1 by 2 plus, now this case when one of them is 8k plus 1, so this probability is 1 by 8 into other one is 8k plus 7, which is 1 by 8 into 2, because x and y, they can be interchanged, and then the second case, which again is into 2, so it will be 4 by 2. So this probability is simply a 1 by 4 plus 1 by 16, which is 5 by 16. So if two numbers are randomly selected, then the probability that sum of their cubes is divisible by 8 is 5 by 16, and that is the answer to this question. Now here the question is, in a multiple choice question, there are 5 alternative answers to which one or more can be correct. A candidate will get marks in the question only if he ticks the correct answers. The candidate ticks the answers at random if the probability of candidate getting marks on the question is to be greater than or equal to 1 by 3. Find the least number of chances he should be allowed. Now in this question, there are 5 alternative answers. So if we look at total number of choices that a student have, then for each option, he has 2 options. Either he can choose it or he can discard it. So there will be 2 into 2 into 2 into 2. There will be total 32 choices. So there will be 32 ways to answer this question, out of which only one is correct. Now we need to find the least number of chances so that his probability of getting marks in the question is greater than or equal to 1 by 3. He'll get marks if he gets it right in the first attempt, which is this probability 1 by 32, or he doesn't get it in the first time, so it'll be this 31 by 32, but he gets it in the second time, which is 1 by 31, or he gets it in the third time, so it'll be 31 by 32 into 30 by 31 into 1 by 30, and it continues n times. Now here 31 will cancel, 31 and 30 will cancel, so this probability will be simply n by 32. Now it says this probability, it should be greater than or equal to 1 by 3. That means value of n, it should be greater than or equal to 32 by 3, which is 10 point something. So that means minimum value of n should be 11. So the probability of the candidate getting marks in the question greater than or equal to 1 by 3, he should be allowed at least 11 chances. And that is the answer to this question. Now here the question is, a certain drug manufactured by a company is tested chemically for its toxic nature. Let the event the drug is toxic is denoted by H and the event the chemical test reveals that the drug is toxic is denoted by S. Now, probability that the drug is toxic, it is A. Now, we are given that probability of S by H equals probability of S naught by H naught. It is 1 minus A. Then show that probability that the drug is not toxic given that the chemical test reveals it is toxic is free from A. So either this drug will be toxic or it is not toxic. Now probability that this drug is toxic, it is given by A. So if it is not toxic, it is given by 1 minus A. Now if it is toxic, then the chemical test reveals that the drug is toxic. It is given by P S by H, and this probability is 1 minus A. Now in this case we are not given that probability S by H naught, but rather we are given probability of S naught by H naught, and this is 1 minus A. Now we know that probability of S by H naught plus probability of S naught by H naught will be probability of S intersection H naught upon probability of H naught plus probability of S naught intersection H naught upon probability of H naught. This is probability of H naught, and this is probability of H naught minus probability of S naught intersection H naught plus probability of S naught intersection H naught. Now it will cancel. So this is 1. So sum of these two probabilities is 1. Now we are given that probability of S naught minus H naught, it is 1 minus A. Then probability of S upon H naught is simply A. Now we need to find the probability that the drug is not toxic given that chemical test reveals that it is toxic. Now it is a Bayes theorem question. So we need to find probability that it is not toxic even though the test reveals it is toxic. So what we'll do is we'll take this case in the numerator. So it'll be this 1 minus A into A in the numerator upon now these two cases in the denominator. So it'll be A upon 1 minus A plus 1 minus A into A, and this is 1 by 2 which is independent of A. So this conditional probability is free from A and its value is simply 1 by 2. Now the next question is, a person has 3 tests in succession. The probability of his passing the first test is P. That of his passing each successive test is P or P by 2 accordingly if he passes or fails in the preceding one. He gets selected provided he passes at least 2 tests. Determine the probability that the person is selected. Now in the 3 tests, this person could either pass all the 3 tests, which is pass, pass and pass, or it could be pass, pass, fail, or pass, fail and pass, or it could be fail, pass and pass. So these are the 4 cases in which this person is going to be selected. Now this required probability for this event, say A, it will be, now for the first test, he passes with the probability P. Now if he passes this first test, then probability of passing the next test, it again is P, and here also it will be this P plus, now passing here is P, next one also will be P, and failing the third will be simply 1 minus P. Now passing the first one, P, failing second, it is 1 minus P, and if it has failed in the second test, then passing this third, it is P by 2. So it will be this P by 2. And here it is failing the first, 1 minus P, passing second, it is P by 2, and then again it is P. So here it will be this P cube plus P square minus P cube, and then here will be P square minus P cube. Now this P cube will cancel. So this probability will be 2P square minus P cube, or simply P square into 2 minus P. And which is the answer to this part A. Now here we have 3 questions, 1, 2 and 3. Now the first question is, 2 non-negative integers are chosen at random from the set of non-negative integers with replacement. if the probability that sum of the squares divisible by 10 is p, then we need to find the value of 50p. Now, if we look at the squares of non-negative integers, then 0 square is 0, 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16, 5 square is 25, 6 square is 36, 7 square is 49, 8 square is 64, and 9 square is 81. Now it says sum of squares is divisible by 10. Now it will be divisible by 10 if we choose both the numbers which are 0. So it will be this combination 0, 0. Or if we choose 1, 9 or 9, 1. So it will be this 1 or 9, or it will be this 4, 6 and 6, 4. So, and then we also have this 5, 5. So it'll be this 5, 5 also. Now if it is 0, 0, now 0 is 1 by 10. Choosing another 0 is 1 by 10. Now 1 and 9. Now choosing 1 is 2 by 10, and choosing 9 is also 2 by 10, and then we have this 9, 1, so it will be this into 2, plus now 4, 6, 4 is 2 by 10, 6 is also 2 by 10, and then into 2, plus 5 and 5, it will be this 1 by 10 into 1 by 10. So this probability will be this 100, and then we have 1 plus 8 plus 8 plus 1, which is 18 by 100, and that is 9 by 50. Now we need to find the value of 50p. So value of 50p is 9, and that is the answer to this question. Now here the question is, a player tosses an unbiased coin and is to score 2 points for every heads turning up, 1 point for every tail turning up. If Pn denotes the probability that his score is exactly n points, then prove that Pn minus Pn minus 1 equals 1 by 2, Pn minus 2 minus Pn minus 1. Now, we know that Pn is probability of scoring exactly n points. Now, a player can score n points if he has n minus 2 points already, and then he gets a head for which he's going to get 2 points, or he has n minus 1 points and then he gets a tails. Now n minus 2 points, it is given by P n minus 2, and probability of getting a heads is 1 by 2, and n minus 1 points is P n minus 1, and probability of getting a tails is simply 1 by 2. Now if we subtract Pn minus 1 from this, we can write Pn minus Pn minus 1, it will be simply 1 by 2 into Pn minus 2 minus Pn minus 1, which is what we need to prove in this question. Now it says also compute P1 and P2 and hence deduce the probability that he scores exactly 4. Now in this case, P1 is he scores exactly 1 point, and it is possible if and only if he gets a tails. So this probability is 1 by 2. Now getting 2 points is either he gets a heads or he gets 2 tails, which is 1 by 2 into 1 by 2, and there will be simply 3 by 4. So now we have the value of P1 and we also have the value of P2. Now Pn is arithmetic mean of these two previous probabilities. So this P3 will be simply 1 by 2 into 1 by 2 plus 3 by 4, which is 5 by 8, and P4 will be 1 by 2 into 3 by 4 plus 5 by 8, and that will be 11 by 16. So the probability that he scores exactly 4 will be given by P4, which is 11 by 16. Maximum of 4 shots at an enemy's plane moving away from it.
The probability of plane hitting at first, second, third and fourth shots are 0.4, 0.3, 0.2 and 0.1 respectively. What is the probability that the gun hits the plane? Now, the probability that this gun it is going to hit the plane will depend on whether target has been hit by the previous shot. Now, the target can be hit on the first shot. In that case, this probability will be simply 0.4 plus. Now, suppose first shot is missed. Now, in this case, this probability will be simply 0.6 into this probability when the target is shot at the second attempt. So, it will be simply 0.3 plus. Now, first two attempts, they fail. So, it will be 0.6 into 0.7 and it is hit in the third shot and there will be 0.2. And this fourth case, when the first three shots are missed, so it will be 0.6 into 0.7 into 0.8 and then it is hit by this fourth shot. So this is the required probability that we are looking at, and if we add them, we'll get this probability as 0.6976. Now another way of solving the same question can be, we can find this probability by using exclusion. So we'll subtract all those cases when the target is missed. So it is missed by all the four shots. So there will be 1 minus 0.6 into 0.7 into 0.8 into 0.9 and this probability again will be 0.6976. Now here the question is, a coin has probability P of showing heads when tossed. When it is tossed n times, let Pn denote the probability that no two or more consecutive heads occur. Then which of the following is true? Now if we toss a coin once, then two heads can never appear. That means this probability 1 is going to be always 1. So this A, it matches with R. Now if we consider P2, in P2 we have two coins tossed. Now we need to find the probability that no two or more consecutive heads occur. Now what we'll do is, in order to find P2, we'll subtract from 1 the case when both of them are heads. Now probability of getting a heads, it is P. So it will be this P into P. So this P2 will be 1 minus P square. So this B, it matches with Q. Now before this third one, we'll take this fourth case when we have Pn. That is, we have tossed n coins. Now suppose we have tossed these n coins. And Pn is the probability that no two or more consecutive heads occur. Now we'll consider two cases. Case 1, when this nth coin shows a heads or when this nth coin shows a tails. Now if the nth coin shows a tails, then for the previous n minus 1 coins, there should be no consecutive heads. So we can write this Pn, if it is tails, now probability of getting a tails is 1 minus P into probability of no consecutive heads in n minus 1 coins. But if it is heads here, then here it must be tails. Otherwise, we'll have two consecutive heads. And if these two are decided, then it can be any configuration in n minus 2 coins. Then it will be this heads, which is P, tails, which is 1 minus P, and then it will be P n minus 2. That means this D, it matches with S. Now once you have this general formula, we can write P3. Now P3 is going to be 1 minus P into P2 plus P into 1 minus P into P1. Now P1 is 1 and P2 is 1 minus P square. So we can write this as 1 minus P, and here it will be 1 minus P square plus P. Now if we simplify this, we can write this as 1 minus P square plus P minus P plus P cube minus P square. Now P and P will cancel, so this probability will be 1 minus 2P square plus P cube, and that's your option P. So this C, it matches with P. And this is the answer to this question.
Now question number 13 says, a box contains exactly 5 chips, 3 red and 2 white. Now it says chips are randomly removed one at a time without replacement until all the red chips are drawn or all the white chips are drawn. What is the probability that last chip drawn is white? Now this last will be white if we get white in first two, or if we get white red and white in third, or if we get white red red and white in fourth. These are three possible cases. Required probability will be, now this is white into white. Now probability of drawing a white chip is 2 by 5 into 1 by 4 plus, in this case it will be 2 by 5, red is 3 by 4 and then white is 1 by 3 into, now this we have two cases, WRW or RWW. So we have to multiply it with 2 and then plus, here it will be 2 by 5, 3 by 4, 2 by 3 into 1 by 2, and here we have factorial 3 upon factorial 2 possible combinations of WRR, so it will be 3, so we have to multiply it with 3. So this value will be simply 1 by 10 plus, now here 3 will cancel, it will also cancel, so this is 1 by 5, here this 4 will cancel, 3 will cancel, and we'll get this as 3 by 10. So it will be 4 by 10 plus 2 by 10. So it will be simply 6 by 10, which is 3 by 5, and that's your option D.
Now in part B it says two squares are chosen at random on a chessboard. What is the probability that they have a side in common? So if we look at a chessboard, then now there are 4 corner squares. So the probability of choosing any one square from these 4 corner squares is 4 by 64. And if we choose corner square, it has 2 neighbors. So if 2 squares, they have a side in common, then we need to choose any one of these 2. So it can be done in 2 by 63 ways. Now next we have the squares which are on the edges, but other than corner squares. Now we have 6 here. We'll have 6 on this side, 6 on this side, and 6 on this other side. So in all, there will be 24 such squares. The probability of choosing any one square from these 24 squares is 24 by 64. Now for each of these squares, we have 3 neighbors, 1, 2, and 3. So we need to choose any one out of 3, which can be done in 3 by 63 ways. And then plus, if we choose any of these squares from remaining squares, now total number of remaining squares will be 6 into 6, 36. So probability will be 36 by 64 into, so each of these squares has 4 neighbors. So we can choose any one out of 4. It can be done in 4 by 63 ways. So this required probability is 4 into 2, 8 plus 72 plus 144, which is 224 upon 64 into 63. Now this is 16 and 8, and this is 8, and this is 7 and 2, and this is 9. So this required probability is simply 1 by 18, and that is the answer to this question.
Now here the question is, if these 3 are probabilities of 3 pairwise exclusive events, then set of all values of PS. Now we know that any probability, it lies between 0 and 1. So this 1 plus 3 P by 3, it should lie between 0 and 1. 1 minus P by 4 should also lie between 0 and 1. And 1 minus 2P by 2 should also lie between 0 and 1. Now from this first one, we will get this case that P is greater than minus 1 by 3 and it is less than or equal to 2 by 3. From this we'll get P lies between 0 and 1, and from here we'll get the condition that P lies between 0 and 1 by 2. And since these events are pairwise exclusive, then probability of A union B union C, which is simply PA plus PB plus PC, which is 1 plus 3P by 3 plus 1 minus P by 4 plus 1 minus 2P by 2. It should also be greater than or equal to 0, but less than or equal to 1. Now this value is 13 minus 3P by 12, and it should lie between 0 and 1. Now from here we'll get this condition that P is less than or equal to 13 by 3, and it should be greater than or equal to 1 by 3. Now if we take intersection of all these conditions, then from here we'll get the value of P. It should lie between included 1 by 3 to included 1 by 2, and that's your option B. Now here the question is, two cards are randomly drawn from well shuffled pack of 52 playing cards without replacement. Let X be the first number and Y be the second number. Now ace is denoted by 1, jack by 11, queen by 12, and king by 13. Find the probability that X and Y satisfy this condition. Now we solve this, we can write this as log 3, and it will be x plus y upon xy. It should be equal to minus 1 or 3 times x plus y. It must be equal to xy. Now from here we can say 3 divides x or 3 divides y. So at least one of x or y, it must be a multiple of 3. So the possible choices for x and y, they are 3, 6, 9 or 12. Now if we choose x as 3, then in that case this 3 and 3 will cancel. We'll get 3 plus y equals y. We'll get 3 equals 0, which is not possible. So x equal to 3 is not possible. Now if we take x as 6, then it will be 3, 6 plus y, and there will be 6y. Now this is 2. We'll get y equals 6. So this is one feasible case when the value of x is 6 and when the value of y is also 6. Now if we take x as 9, here it will be 3 into 9 plus y, and it will be equal to 9y. Now this is 3. We'll get 2y equals 9. We won't get any integral value. So again x equal to 9, it is not possible. And finally we have x equals 12. Now if we put x as 12, it will be 3 into 12 plus y equals 12y. Now this is 4. So we'll get 3y equals 12. Value of y is 4. So we get our second case when x is 12 and y is 4. Now since there is symmetry in the problem, we can consider the same analysis for y. So again we'll have x equals 6 and y equals 6, and we'll have one more case when x is 4 and y is 12. So these are the 3 feasible solutions possible for this problem. Now we need to find its required probability. Now this required probability will be given by, now probability that x is 6. So this probability will be simply 4 by 52, and then into next one is also 6, and there will be 3 by 51 plus. Now x equals 12, so it will be 4 by 52, and y equals 4, which again is 4 by 51. Now this is 4, so 4 by 52 and 12, then 4 by 51. So this required probability will be 52 into 51, and that is 16, 16, 32, 32 plus 12, and that will be 44. Now this is 11,
and this is 13. So this required probability is 11 upon 663, and that is the answer to this question. Now it says let P be the probability that a man aged X years will die in a year time. The probability that out of n men, A1, A2 and An, each aged X years, A1 will die and will be the first to die is. Now if A1 has to die, then in the next year, at least one person must die. So what is the probability that at least one person must die? So this probability is 1 minus no one dies. So probability of dying is P and probability of not dying is 1 minus P. So there are n people. So this probability will be 1 minus P, n times. So this is the probability that at least one of them is going to die. Now we need to find this probability that A1 will die and will be the first one to die. Now the first person to die could be any one of A1, A2, A3 up to An. So total we have n choices, and if A1 has to die, then in that case, favorable case, it will be simply 1. So the probability that A1 will die and will be the first one to die will be 1 by n into 1 minus p to the power n, and that's your option D. Now here the question is, the probability of India winning a test match against West Indies is 1 by 2. So probability of India winning, it is 1 by 2, and assuming independence from match to match, we need to find the probability that in a match series, India's second win occurs at third test. I think it should be in a 3-match series. Now second win should occur at third test. So either it could be win, loss and win, or it could be loss, win and win. So these are the only two possibilities. Now first one is 1 by 2 into 1 by 2 into 1 by 2 and plus 1 by 2 into 1 by 2 into 1 by 2. So it is nothing but 1 by 4, and that's your option 2. Now the question is, in a multiple choice question, there are 4 alternate answers out of which 1 or more are correct. A candidate will get marks in the question only if he takes. A candidate decides to take answers at random. If he is allowed up to 3 chances to answer, he'll get marks in the question. Now, if it has 4 alternatives, then total number of possible choices are, for each option we have 2 choices. So it'll be 2 into 2 into 2 into 2. So there'll be 16 choices, but then there'll be this one choice when none of the answer is correct, which is not possible. So it should have at least one answer. So total choices we have here is 15. Now out of these 15, we have 14 wrong choices and 1 correct choice. So from these 15, he can try any 3. So it'll be 15C3, and among these 3, one of them has to be the correct one. So it'll be this 1C1, and then it'll be 14C2. Now this is 14 into 13 by 2, and this is 15 into 14 into 13, and this is 3 into 2. Now he'll cancel, 2 will cancel. So this probability is simply 3 by 15 or 1 by 5, and that's your option 3. Now it says, in a transaction process consisting of 3 activities, namely allocation, task processing and quality checks. So we have allocation, task processing and quality check. 9 employees including 5 male and 4 female. So we have 5 males and 4 females who are working. 2 of them are process leads, 4 perform processing, remaining 3 are quality auditors. Now out of the 4 female employees, 1 is a process lead. So we have 1 male processing lead and 1 female processing lead. 2 are processing executives. So we'll have 2 and 2 here, and then the remaining 1 is a quality auditor. So one of the female is quality auditor, whereas we have 2 male quality auditors. Now suppose the chance of allocating a task is equal among the process leads, equal among processes and equal among quality checks. What is the probability that the task is completely handled by a female employee? Now for this, required probability will be auditor has to be female. Here we have 2 people, out of which 1 is female. So this probability will be 1 by 2 into. Now for the second one, this probability will be simply 2 by 4, which again is 1 by 2, and for quality it is 1 by 3. And the process of choosing an employee across any process, it is independent. So this required probability is simply 1 by 12. Now here the question is, let U1 and U2 be two urns such that U1 contains 3 white and 2 red balls, and U2 contains only 1 white ball. Now a fair coin is tossed. If head appears, then 1 ball is drawn at random from urn 1 and put into urn 2. And if tail appears, then 2 balls are drawn at random from U1 and put into U2. Now 1 ball is drawn at random from U2. The probability of the drawn ball from U2 being white is. Now what we'll do is, first we'll toss a coin and it will result in either heads or tail. So probability of getting a heads is 1 by 2 and probability of getting a tail is 1 by 2. Now if it is head, then 1 ball is drawn at random from U1 and put into U2. So this 1 ball, it could be either white or red. Now probability of getting a white ball, it is 3 by 5 and red ball is 2 by 5. Now if it is head, U2 will have 2 white now, and if it is red, it will have 1 white and 1 red. Now 1 ball is drawn from U2. We need to find the probability that drawn ball is white. Now if it is 2 white, then probability of drawing a white ball, it is 1. And if it is 1 white and 1 red, this probability will be 1 by 2. Now if the coin results in tail, then we have 3 choices. Either the transferred balls will be 2 white or 2 red or 1 white and 1 red. Now probability of choosing 2 white will be 3C2 upon 5C2. It will be 3 by 10. Now 2 red, 2C2 upon 5C2, 1 by 10, and 1 white and 1 red, there will be 3C1 into 2C1, which is 6 by 10. Now if it is 2 white, urn 2 will have 3 white now, or it will have 1 white and 2 red, or it will have 2 white and 1 red. Now probability of getting a white ball, here in this case is 1, here will be this 1 by 3, and here will be this 2 by 3. Now first we need to find the probability that white ball is being drawn from. So probability that it is a white ball which is drawn from U2. Now basically it's a conditional probability, so we have to multiply all these probabilities. So it will be this 1 by 2 into 3 by 5 into 1 plus 1 by 2 into 2 by 5 into 1 by 2 plus 1 by 2 into 3 by 10 into 1 plus 1 by 2 into 1 by 10 into 1 by 3 plus 1 by 2 into 6 by 10 into 2 by 3. Now this is 3 by 10 plus 1 by 10 plus 3 by 20, 1 by 60, 2 by 10. Now this is 6 by 10, 36 by 60, 9 by 60 plus 1 by 60, which is 46 by 60. Now this is 23 by 30, and that's your option B. Now the second part is, given that the drawn ball from U2 is white, the probability that head appeared on the coin is. Now this is Bayes' theorem. So you have to find, if it is a white ball, then head appeared on the coin. So this case of heads, it should be in the numerator, and this total probability will be in the denominator.
Now this probability of heads, it is these first two terms, which is 4 by 10. So it will be 4 by 10 divided by 23 by 30. So it will be simply 12 by 23, and that's your option D. Now here the question is, if A, B, C are natural numbers, then the probability that A square plus B square plus C square is divisible by 7 is m by n, then m plus n is equal to. Now we know that we can write any number as 7m plus r whole square, and 7m plus r whole square, it is r square remainder r dash modulo 7, where r, it takes the value from 0 to 6. Now when r square is 0, it is 0 modulo 7. If it is 1, it is 1 modulo 7. 2 square is 4 modulo 7. 3 square 9. 9 is 2 modulo 7. 4 square is 16, which again is 2 modulo 7. 5 square is 4 modulo 7. And 6 square is 1 modulo 7. These are the possible remainders for 7m plus r, where r can take these 7 values. Now it says we need to find the probability that a square plus b square plus c square is divisible by 7. Now it will be divisible by 7 if all of them, they are 0 modulo 7, that is this case, or when it is 1, 2 and 4. So in that case, it will be 1 plus 2 plus 4, 7, which again is 0 modulo 7. So some of these three squares, they will be divisible by 7 in these two cases. For A to have 0 modulo 7, it should be 7m plus 0. So value of r, it should be 0. So in that case, this probability is 1 by 7. Now for B also, it will be 1 by 7, and for C also, it will be 1 by 7. So for this first case, this required probability will be 1 by 7 cube. Now for this second case, modulo 1, we have two cases. So there will be 2 by 7. Modulo 2 is again two cases. So there will be 2 by 7. And modulo 4 is also two cases. So there will be 2 by 7. And out of these A, B and C, anyone can have 1, 2 and 4. So we can distribute it in factorial 3 ways. So it will be 48 upon 7 cube. So this required probability is sum of these two, which is 49 by 7 cube, which is nothing but 1 by 7, and that's your m by n. Now the value of m plus n is simply 8. So answer to this question is 8. Now here the question is, football teams T1 and T2 have to play 2 games against each other. So they have to play 2 games. Now it is assumed that outcome of the 2 games are independent. The probability of T1 winning, drawing and losing, they are 1 by 2, 1 by 6 and 1 by 3. Now each team, they get 3 points for a win and 1 point for a draw and 0 for a loss. Let X and Y denote total points scored by teams T1 and T2. Now we have to find the probability that X is greater than Y. Now we have this scenario when team 1, it wins both the matches. In this case, this team, it will have 6 points. T2 will have 0 points. And there could be, there is a win and a draw. Here will be loss and a draw. Now win and a draw is 4 and here it is 1. So in both the cases, X is greater than Y, and these are the only 2 cases possible. Now we'll calculate this probability X is greater than Y. Now if it is 2 wins then it will be this 1 by 2 into 1 by 2 plus now a win and a draw. Now which one is a win? So it will be this 2C1, and probability of winning is 1 by 2, and probability of making a draw, it is 1 by 6. Now this 2 and 2 will cancel. Now we'll get this as 12. So this probability will be 5 by 12, and that's your option B. Now we have the second case when the value of x is equal to value of y. Now again for this we have two cases. Either it will be this win-lose, lose-win, or it will be both draws. Now in this case it will be 3-3, and here it will be 2-2. Now if we have to calculate this probability when the value of x is equal to y, that will be a win and a loss. Now which one is a win? So it will be this 2C1, and probability of winning is 1 by 2, and probability of losing is 1 by 3, plus now both draws, it is 1 by 6 into 1 by 6. Now this 2 and 2 will cancel. Now this is 36, 12 plus 1, 13. So this value will be 13 by 36, and that's your option C. Now here the question is, if m into n coins have been distributed into m purses, n into each, now we need to find the probability that two specific coins A and B, they are in the same purse. Now what we'll say is, suppose we have these coins distributed in these n purses, and there are m into n positions. Now in one of the purses we'll have A. Now suppose A is present in this purse. For B to be present in this purse, B can be there in any one of the remaining n minus 1 places. So number of favorable places for B will be simply n minus 1, whereas total number of places will be simply m into n minus 1. So this probability that two specific coins will be found in the same purse is given by n minus 1 upon m into n minus 1, and that's our part 1. Now second part is what the chance becomes when R purses have been examined and found not to contain either of the specific coins. Now here there will be two cases. Case 1, when both the coins they are together, and this second case when they are in separate purses. Now this probability that they will be together, it is given by n minus 1 upon m into n minus 1, and the probability that they will be in separate purse will be given by 1 minus p, and it will be m n minus 1 minus n plus 1 upon m n minus 1. Now 1 and 1 will cancel, so we can write this as n into m minus 1 upon m into n minus 1. Now when A and B are together and R purses have been examined, then the probability that they occur in the remaining m minus R purses will be given by m minus R by n. So total we have m choices, and the favorable cases, they are not present in the first R purses. Now in this case, say P2. Now P2 is when both of them they are in separate purses, but still they are not in first R. So here it will be this MC2. So any two or these M, and then it will be this M minus R C2, which is M minus R, M minus R minus 1 divided by 2. Now 2 will cancel, and here will be this M into M minus 1. So if they are together, then the probability that they'll be in R purses, it is given by M minus R by M. And if they are not together, then the probability that they'll be in remaining M minus R purses will be given by M minus R into M minus R minus 1 upon M minus 1. Now we need to find the probability that they are in the same purse, provided both of them they are not there in the R purses that have been examined. So that means we have to find this probability that they are in the same purse when we have examined R purses. So now it becomes a Bayes theorem question. So this case it'll come in the numerator, so it'll be this n minus 1 upon mn minus 1 into m minus r by m. So it'll be this n minus 1 upon mn minus 1 m minus r upon m plus this case where it is n into m minus 1 upon mn minus 1 into m minus r minus 1 divided by m into m minus 1. Now here m minus 1 and m minus 1 will cancel. N minus 1 and m, it will also cancel. So this required probability will be n minus 1 into m minus r, and the denominator will take m minus r common, and then will be this n minus 1 and plus n into m minus r minus 1. Now m minus r will cancel, so we can write this as n minus 1 upon, and this is n minus 1 plus mn minus nr minus n. Now this n and n will cancel, so this probability will be n minus 1 upon mn minus nr minus 1. And that is the answer to this question.
Now here we have a matching question, and it says in a tournament there are 16 players, S1, S2, S3 up to S16, and they are divided into 8 pairs at random. From each game, a winner is decided on the basis of game played between the two players of the pair. Now assuming that all the players have equal strength, first one is we need to find the probability that S1 is one of the winners. Now in the first phase we have divided the 16 players in 8 random pairs. Now this S1 will be paired with randomly against any player Si, where I varies from 2 to 16. Now S1 is going to be among the winners if S1 wins his or her match against Si, and probability of S1 winning against Si, it is 1 by 2. So clearly this probability of S1 is one of the winners, it is 1 by 2. So this A, it matches with Q. Now B is the probability that exactly one of S1 or S2 is a winner. Now in the second case, we have two scenarios. Scenario 1 is if S1 and S2 they are paired against each other, or this case where they are not paired against each other. Now if we look at this first case when S1 and S2 they are paired opposite each other, then if we take S1, then there are 15 possible pairing combinations for S1, and from these 15 we get S1, S2 if we have S2 as an opponent. So this probability will be simply 1 by 15. Now in this case, probability of winning exactly one of them, it is simply 1. Now if we take the second case when they are not paired against each other, it will be this 1 minus 1 by 15. Now in this we have two possibilities, when S1 wins and S2 loses, or S2 wins and S1 loses. So it will be this 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2. So this probability will be 1 by 15 plus 14 by 15 into, now this is 1 by 2. So this is simply 8 by 15. So this B, it matches with B. Now this third case is both S1 and S2 are among 8 winners. Now they cannot be among 8 winners if they are paired opposite each other. So that means in this third case it is clear that S1 and S2 they must not be paired against each other. Now this probability that they are not paired against each other, it is 1 minus 1 by 15 into, now S1 must win, so it will be this 1 by 2, and S2 must also win, it will be 1 by 2. So this probability will be 14 by 15 into 1 by 4, which is 7 by 30. So this C, it matches with R. And finally, when we have this D, which is both S1 and S2 are not among winners. So in this case also, they cannot be paired against each other. So for this fourth one, again we have S1 and S2 not playing against each other. So this probability will be 1 minus 1 by 15 Now, in its pair, S1 must not win and S2 must also not win. Now, this probability is same as that of third. So, this again will be 7 by 30. So, this D, it also matches with R.
Now, here the question is, a chess match between two grandmasters X and Y is won by whoever wins first a total of 2 games. X chances of winning, drawing and losing are A, B and C respectively, and they are A plus B plus C equals 1, and games are independent. So that means winning, drawing and losing, they are mutually exclusive and exhaustive. Now, first one is find the probability that X wins the match after n plus 1 games. Now, X is going to win after n plus 1 games if in the n plus 1th game X wins and in the remaining n matches it should be 1 win for X and it could be n minus 1 draws, or it could be 1 win for X, 1 win for Y and n minus 2 draws. So these are the possible ways in which X can win the match after n plus 1th game. Now let us call this probability as P n plus 1. Now one match, 1 by X. Now which one? So it will be this NC1 and then it will be this A. N minus 1 draws. So it will be B to the power of n minus 1 and then n plus 1th game A wins. So it will be this n times A square B to the power of n minus 1 plus the second case 1 win NC1. Now 1 win for Y, n minus 1 C1. Now this is A, this is C, B to the power n minus 2 and again n plus 1th win. So it will be this A, so it will be plus n minus 1 A square C B to the power of n minus 2. Now we can take A square common. So if we take A square common, we can write this as, now here will be this n B to the power of n minus 1 plus n minus 1 B to the power of n minus 2 into C, which is A square n into B to the power n minus 1 and n minus 1 B to the power n minus 2 into C, which is your option B. Now in the second question it says the probability that Y wins the match after 4th game. Now we have already calculated it for X, and the difference between X and Y is their probabilities of winning and losing are interchanged. So we'll actually use formula in first to calculate this probability of Y winning in 4th match. So it will be this P4 for Y, and in this we need to interchange A and B. So we can write C square. Now here value of n, it should be 3. So it will be this 3 B square plus 6b, and then we'll interchange C with A. So it will be this A. We'll take 3b common. So it will be this 3bc square, and then here will be this b plus 2a, and that's your option A. Now we look at this option 3. Now option 3 is probability that X wins the match. Now X is going to win the match when the value of n varies from 2 to infinite. So this probability that X wins the match will be this probability n varies from 1 to infinite Pn plus 1, which is A square into this summation n varies from 1 to infinite n B to the power of n minus 1 plus A square C into this summation n varies from 1 to infinite n minus 1 B to the power of n minus 2. Now we have to calculate the sum of these two series, this one and this one. Now, if we look at the series, which is 1 plus b square up to infinite, we know that this is 1 upon 1 minus b, or we can write this as summation b to the power n, where n varies from 0 to infinite. It is 1 upon 1 minus b. Now we differentiate this both sides with respect to b, we'll get this summation. Now n varies from 1 to infinite, n b to the power of n minus 1, and here it will be 1 upon 1 minus b square. So this expression for the first series will be a square upon 1 minus b square. Now here it is a square c. Now we'll differentiate it again. Now if we differentiate this again, we'll get this as n varies from 1 to infinite, n minus 1, b to the power of n minus 2, and here it will be 2 upon 1 minus b cube. So it will be this 2a square c upon 1 minus b cube. Let me simplify this. We can write this as 1 minus b cube, and then it will be this a square into 1 minus b plus 2 into a square c. Now 1 minus b is actually a plus c, so we can write this as a square a plus c plus 2a square c, and here it will be this a plus c whole cube. Now we can take a square common, so it will be this a square, and then it will be a plus 3c upon a plus c whole cube, which is your option B. Now the next one is the probability that y wins the match. Now we know that situation for x and y is exactly same, except for a and c must be interchanged. So if we interchange a and c, we'll get this as c cube plus 3c square a upon a plus c cube. That means this option B, it should be correct. And then finally, we need to find the probability that there is no winner. Now, if we add these two cases, then it will be a cube plus c cube plus 3a square c, 3ca square, which is a plus c whole cube. So sum of these two probabilities is 1. So that means these two probabilities, they are mutually exclusive and exhaustive. So out of x and y, there will be exactly one winner. So probability that there will be no winner is simply 0, and that's your option D. Now here the question is, a coin is tossed n plus n times where m is greater than n. Then we need to show that probability of at least m consecutive heads is. Now this coin, it is tossed m plus n times. M consecutive heads, they may start from this first place, or they may start from the second place, or this third place. So they may start from any place from 1 to n plus 1. Now if m consecutive heads, they start from this first place, from this place, now it should be heads here. So we'll have heads in m consecutive positions. So for each head, we have 1 by 2 possibility. So it will be 1 by 2, 1 by 2, 1 by 2, m times. So if these consecutive heads, they start from first place, this probability is 1 by 2 to the power m. Now, if these heads, they start at second place. Now clearly this first one, it has to be tails now. So this probability is 1 by 2, and again these m consecutive heads will be 1 upon 2 to the power m. So it will be this 1 upon 2 to the power of m plus 1. Now if we look at this third place, now before third, it should be this tails. So again it will be 1 upon 2 to the power of m plus 1. So for any I between 2 and n plus 1, the probability that m consecutive heads start at ith place will be 1 upon 2 to the power of m plus 1. So this required probability will be 1 upon 2 to the power m plus 1 upon 2 to the power of m plus 1, 1 upon 2 to the power of m plus 1 n times. So it will be this n into 1 upon 2 to the power of m plus 1, which is simply n plus 2 upon 2 to the power of m plus 1, which is what we need to prove in this question. Now here the question is, let Pn be the probability that n throws of fair die contains an odd number of 6s. Now probability of getting a 6, it is 1 by 6, and probability of not getting a 6 is 5 by 6. Now if we throw n dice, then we can write this as q plus p to the power n, and it will be nc0 q to the power n plus nc1 q to the power n minus 1 p, nc2 q to the power n minus 2 into p square, and if we take q minus p, it will be q minus p to the power n, nc0 q to the power n minus nc1 q to the power n minus 1 p, and so on and so forth. Now it says Pn is the probability that it contains odd number of 6s. So odd number will be 1, 3. That means we need to find some of these even number terms, second term, fourth term. So what we'll do is we'll subtract these two. If we subtract, we can write q plus p to the power n minus q minus p to the power n, and it will be equal to 2 times nc1 q to the power n minus 1 p, nc3 q to the power n minus 3 p3. Now p plus q is 1 and q minus p is 4 by 6, which is 2 by 3. So it will be this 2 by 3 to the power n, and this is equal to 2 times pn. So basically in this, pn is 1 by 2 into 1 minus 2 by 3 to the power n. Now if we look at pn minus 1, pn minus 1 will be 1 by 2, 1 minus 2 by 3 to the power n minus 1. Now from the first one we can write 2 by 3 to the power n will be 1 minus 2pn, and from second we can write 2 by 3 to the power n minus 1 will be 1 minus 2 p n minus 1. Now we multiply 2 by 3 in the second, we can write 2 by 3 to the power n, and it will be 2 by 3 1 minus 2 p n minus 1, which is equal to 1 minus 2 pn. So it will be 1 minus 2 pn. Now if we cross multiply, we can write 2 minus 4 pn minus 1 will be equal to 3 minus 6 pn, or we can write 6 pn minus 4 pn minus 1 minus 1 equals 0, and that's your option A.
Now here the question is, a slip of paper is given to person A, who marks it with either a positive or a negative sign. The probability of his writing a positive sign is 1 by 3. Now A passes the slip to B, who may leave it alone or change the sign before passing it to C. Similarly, C passes the slip to D, and D passes the slip to referee, who finds a plus sign on the slip. If it is known that B, C and D each change the sign with the probability of 2 by 3, find the probability that A originally wrote a positive sign. Now the slip of paper, it starts from A and it goes to B and then to C and then to D, and thereafter it goes to this referee. Now this A, it can either make a plus sign, we say this event is A positive, or it can start with a negative sign, which is A negative. First what we'll do is we'll find this probability that when referee receives the card, it is a positive sign, which is E plus. Now it will depend on whether A starts with plus or whether A starts with minus. Now if A starts with plus, then it will be a positive sign in two cases. Case 1, when each of B, C and D, they don't change the sign, or exactly 2 of them change the sign. So if they do not change the sign, then it goes from positive to positive, or if 2 of them, any 2 of them, either BC, CD or BD, they change the sign, then again it'll be this plus sign. And if it is negative, from negative to positive, again we'll have 2 cases. Case 1, when exactly one of them changes sign, and when all 3 they change sign. So these are the 4 cases possible. So first we'll find this probability of getting a plus sign. Now, probability of A marking it positive is 1 by 3. And the first case, B, C and D, they do not change. So it will be this 1 by 3 into 1 by 3 into 1 by 3 and then plus. Now again, A starts with positive. So this is 1 by 3 into exactly 2 of them change. So which 2? So it will be this 3C2, and then if 2 of them they change, it will be this 2 by 3 into 2 by 3 and then into 1 by 3. Now this is 3 to the power 4, and here it is 3, 12 and 13. So this probability is 13 upon 3 to the power 4. Plus this second case, when A starts with a negative sign. Now if A starts with a negative sign, this probability will be 2 by 3. So now it is 2 by 3 into exactly one of them changes it. So this is 3C1 and then it will be 2 by 3 into 1 by 3 into 1 by 3 plus 2 by 3 and then all 3 of them they change the sign. So it will be 2 by 3 into 2 by 3 into 2 by 3. So it will be this plus. Now this again is 3 to the power 4. Now this is 12 and 16. So it will be this 28. Now we need to find this conditional probability that if referee receives a plus sign, then A started with a positive sign. So we take this positive sign case in the numerator, which is 13 upon 3 to the power 4 divided by this whole case, which is 28 plus 13, 41 by 3 to the power 4. So this required probability is 13 by 41, and that is the answer to this question. Now here the question is, a coin has probability P of showing heads when tossed. So probability of getting a heads, it is P, and probability of getting a tails, it is 1 minus P. Now it is tossed n times. Now Pn denotes the probability that no 2 or more consecutive heads occur. Now if you look at P1, that means this coin is tossed once. So in that case, either way, heads or tails, it will satisfy the condition. So this P1 will be 1. Now if we look at P2, P2 will be the case when we have either heads tails or tails heads or tails tails. That is 1 minus this case when it has turned heads both times. So it will be this 1 minus P square. So that's your P1 and P2. Now if we look at Pn, now Pn is n tosses, and in these n tosses there should be no 2 consecutive heads. Now if we look at this Pn for this nth toss, suppose this is this nth toss, it can result in either heads or tails. Now if it has resulted in heads, here it must be tails. Now here it could be anything. Now this arrangement is nothing but this is Pn minus 2. So it will be this Pn minus 2 into this probability of getting a tails, which is 1 minus P, into probability of getting a heads, which is P. And then plus, if it is tails here, then the previous one, it could be either heads or tails. Now this is nothing but this is Pn minus 1, and then the probability of getting a tails, it is 1 minus P. So this Pn will be 1 minus P into Pn minus 1 plus P into 1 minus P into Pn minus 2 for all n greater than or equal to 3, and which is what we need to prove in this question. Now here the question is, 15 coupons are numbered from 1 to 15 and 7 coupons are selected at random, one at a time with replacement.
the probability that largest number appearing on selected coupon is 9. Now, if the coupon has all the numbers from 1 to 9, we have 9 favorable cases. So this required probability will be 9 divided by 15 for each ticket, and there are 7 tickets or 7 coupons. So there will be 9 upon 15 to the power 7. Now in this case, since the largest number has to be 9, so that means there has to be at least one 9 in the selected coupons. So from this, we'll subtract all those cases in which we have no 9. So then we'll have this probability 8 by 15 to the power 7. So this required probability will be 9 to the power 7 minus 8 to the power 7 divided by 15 to the power 7, and that's your option D. And this question, it says 2 players P1 and P2 play a game against each other. In every round of game, each player rolls a fair die once. When the 6 faces of die have 6 distinct numbers, let X and Y denote readings on the die rolled by P1 and P2. If X is greater than Y, P1 scores 5 points and P2 scores 0. If X is equal to Y, then each player scores 2 points. And if X is less than Y, then P1 scores 0 and P2 scores 5. Now let Xi and Yi be the total scores of P1 and P2 respectively after ith round. Then we have to match these probabilities. Now in any round, both P1 and P2, they're going to roll a die, and suppose numbers they get is X, Y. Now total combinations possible is 36. Now out of these 36, we'll get X equals Y if we have 1, 1, 2, 2 up to 6, 6. So this probability that both the numbers they'll be same, or we'll say this is a drawn case. In this case, it will be simply 6 by 36, which is 1 by 6. In the remaining 30 cases, from symmetry we can say in half the cases, that is in 15 cases, X will be greater than Y, and in 15 cases, X will be less than Y. So probability of player 1 winning, it will be 15 by 36, which is 5 by 12, and player 1 losing, it will also be 5 by 12. So in each round, the probability that they'll draw, it is 1 by 6. Probability that player 1 is going to win is 5 by 12, and probability that player 1 is going to lose is also 5 by 12. Now we look at this probability x2 is greater than or equal to y2. Now this probability is after 2 rounds, score of P1 is either greater than or equal to score of player 2. Now this can happen if it is win in both rounds, or it is win and draw. Now win and draw, it can be either win draw or draw win. So it will be these two cases, plus the score may be equal if there is 1 win and 1 loss. Again it will be win loss or loss win, so it will be into 2, and plus both draws. So these are the 4 cases in which score of P1 will be greater than score of P2 after 2 rounds. Now probability of winning is 5 by 12, so it will be 5 by 12 into 5 by 12 plus 2 into winning 5 by 12, drawing 1 by 6, 2 into probability of winning 5 by 12, losing 5 by 12, and plus probability of drawing, which is 1 by 6 and 1 by 6. Now this is 25 by 144. This is 20 by 144. (50 by 144) and 4 by 144. Now this is 99 upon 144, which is 11 upon 16. That means this first one, it matches with Q. So this first bit matches with Q. Now, second one is probability of x2 greater than y2. Now, for x2 greater than y2, we'll take out those cases in which they'll have equal scores. So, we'll take out these two cases. So, it'll be this condition, which is 25 by 144 plus 20 by 144, which is 45 upon 144. Now this is 5 by 16. So this second one, it matches with R. So this second, it matches with R. Q, R, Q and R. Now this third one is probability that x3 is equal to y3. That means we have to find the probability that after 3 rounds, both of them, they'll have equal scores. So probability of x3 equals y3. Now they'll have equal scores if all the 3 matches are drawn, or there is 1 win, 1 loss and 1 draw. And we can arrange these 3 in factorial 3 ways. Now this is 1 by 6 into 1 by 6 into 1 by 6, and this is 6 into, now winning is 5 by 12, losing is 5 by 12, and drawing is 1 by 6. Now this is 144 into 6, and this is 4 plus 150, so it will be this 154 upon 144 into 6. Now this is 77 and this is 3, so it will be this 77 upon 432. That means this third one, it matches with T. So this third, it matches with T. And the fourth one is probability of x3 greater than y3. For this fourth one, we have this probability of x3 greater than y3. Now it will be greater if it is all 3 wins or 2 wins and 1 loss, and they can be arranged in factorial 3 divided by factorial 2 3 ways, or 2 wins and a draw. Again, it can be arranged in 3 ways, or a win and 2 draws. Again, it can be arranged in 3 ways. So these are the 4 possible cases. Now all 3 wins, so it will be 5 by 12 into 5 by 12 into 5 by 12. Now this is 3 into 5 by 12 into 5 by 12, and 1 loss is also 5 by 12 plus 3 into 2 wins, 5 by 12 into 5 by 12 into 1 by 6, and plus 3 into 1 win, which is 5 by 12, and then 1 by 6 into 1 by 6. Now this is 125 upon 1728 plus 375 upon 1728 plus 150 upon 1728 plus 60 upon 1728, and there will be 710 upon 1728. Now we cancel with 2. This is 355 and this is 864. So this value, it will be 355 upon 864. That means this fourth, it matches with S. So the correct option is this option A.